We're going to move on now to some examples of related rates that have to do with triangles. Specifically, I want to talk about the ladder problem, which is probably one of the most common related rates problems to show up on the AP exam. So, in terms of related rates problems and word problems, I want to go over procedure again. If possible, draw a diagram for the problem. If it has anything to do with something that's not just a strict geometric shape, like a circle changing or a cube changing, a diagram really helps. And I put in red here, what is most important about your diagram is that it absolutely has to show what's changing, and it has to use variables to record those changes. So what I mean by that is, once you've got your diagram drawn, use variables to represent all of the side lengths. Like even if you know they say, oh yeah, that's 5 units long, use a variable for it, because that allows us to talk about how it might change. Once you have those variables, we can write an equation that models the relationships between them. In other words, come up with an equation that involves all the variables you just wrote down. And then we differentiate the equation with respect to time and solve for the quantity that they want us to solve for. So in general, that's what we're going to do. Let's move on to the ladder problem. So if I have a 13-foot long ladder that's leaning against a building, right? So the premise here is that there's a building. It's kind of a slanted building, I suppose. So there's this building, and there's a 13-foot ladder that's leaning against the building. So here I have this ladder that's leaning against the building. Now we know this ladder is 13 feet long, and so a lot of people are inclined to write a 13 over here. And I'm okay with that, but I believe that we need to say that this is equal to a variable. Now it may be that it's constant, but we still need to have a letter for it. Okay? So 13-foot ladder leaning against the building. The top of the ladder begins sliding down the wall at a rate of 0.5 feet per second. So that means this point up here at the top begins sliding down the wall. So the question that you need to work out, and the thing that I want you to think about, is what does this 0.5 represent? Like, how am I going to write it down? In particular, what label am I going to give to it? Over here, when I picked 13, I decided to call that C. So what label will I give to this 0.5 feet per second? Pause the video and think about that for a second. The idea is, that's a rate. It says 0.5 feet per second, right? It says it's moving down at a rate of that. So what I need to say over here is something like, dB dt. If you said dA dt, that's fine. So dB dt is negative 0.5. And that negative didn't come out very well. Negative 0.5. Now why is it negative? And this is an important thing. It's not negative because it's moving downward. It's negative because this length over here, this b, whatever b may be, this length is getting shorter. And because that length is decreasing, my rate is negative. And the question is asking, how quickly is the base of the ladder sliding away from the wall? Now, again, pause the video, think for that for a minute. What does that represent? How are you going to write that down? What is the question asking for? The question is asking for, this part of the movement down here. What is dA dt? How quickly is that side getting longer? And it says, how quickly is the base of the ladder sliding away from the wall when the base of the ladder is 5 feet from the wall? So that means we know that A is 5. Right? So here I am sort of looking at this information, right? I have that this length is 13. I have a rate over here, but not a length. I want to find this rate, and I have this length. At this point, we need to sort of go in and sort of flesh out the other information here, right? So for instance, over here, it's good for us to know what dC dt is. Any variable that you have should have a rate associated with it. So now here's where I'd like you guys to pause the video and think for a minute. What is dC dt? Think about what that represents, think about what it means, and then think about the fact that it's a ladder, and decide for yourselves what dC dt is. I hope you determined that dC dt was 0. Because C isn't changing. C is a 13-foot long ladder. It's not like it's getting shorter or getting longer as it's sliding on the wall. It's staying 13 feet long. It is not changing, which means its rate of change is 0. Now this one down here we're going to have to leave blank because that's what we need to solve for. But it is troublesome that I don't have a value of b over here. Fortunately, we have the Pythagorean theorem. And this is actually a Pythagorean triple. We have 5, 12, 13. So at this point I have all of my information. Now I just need an equation that will relate all of the information that I have. And I think the best equation for us to use is the Pythagorean theorem. we can use that a squared plus b squared equals c squared. So now that I have that, we should be able to take the derivative with respect to t and then use the numbers that we have. And so I really believe that you guys should be able to do this, so pause the video and try that out. When you take the derivative, you should get 2a dA dt plus 2b dB dt equals 2c dC dt. At this point, we could actually divide out the 2 because all the terms have a 2 in them. And now it's just a matter of evaluating using all the numbers that I have. We know that a is 5. We know dA dt is what we're solving for. B is 12. dB dt is negative 0.5. And on the other side, we have c times dC dt, so we have 13 times 0. So we're going to end up with 0 on the other side. So solving this, I have 5 dA dt minus 6 equals 0. That means dA dt is 6/5. And that's our answer. This ladder is sliding down the wall at a rate of, negative, rather a half a foot per second, sliding downward. That's why it's negative. And so this is actually sliding away from the wall at a rate of, 6/5 or 1.2 feet per second. Okay, so that's the ladder problem. This is sort of the way these things are set up and the way that it works. Now I have a little bit of a twist on the problem, right? I want the same ladder. The top of the ladder is still falling at the same rate, still a half a foot per second. But now I'm asking, how fast is the angle the base of the ladder makes with the ground changing, right? So we can still set this thing up. I've still got my building. It's a skinnier building now. I still have a ladder leaning against the building. C is still 13. dC dt is still 0. Over on, I'm going to have to move this a little bit. Over on this side, we still have dB dt coming in at negative 0.5. In some sense, we still know that b is 12, right? Down here on the bottom, we still know that a is 5. But this question is now asking about the angle that the base of the ladder makes with the ground. It's this angle down here that we're interested in. And in particular, what we're interested in is we're interested in d theta dt. Okay? So I need an equation. Like, now that I've got all this stuff set up, I need an equation that will tie together these roots. No, not roots, but rates, sorry. That will tie together these rates. I need an equation that will have b and c and theta in it. And so I want you guys to think for a minute, like pause the video, think for a minute. Do you know of any equations that could relate the length of this side, the length of this side, and this angle? So pause the video and think about that. I hope you came up with it. I hope you came up with the idea that, hey, sine should work really well. If I worked with the idea that sine theta was opposite over hypotenuse, that would be b over c. Right? I now have an equation that will relate all of the information that I have. Right? So now how do I go through and actually do this problem? How do I solve this thing? Well, I'm supposed to take this equation and I'm supposed to take the derivative with respect to t. Right? So when I take this derivative with respect to t, I'll sort of bring it down here. The left-hand side will give me cosine theta times d theta dt equals. Now on the right side, I'm going to need to do a quotient rule. And so we're just going to have to walk through this carefully. It'll be low d high, so c times dB dt, minus high d low, that's dC dt, all over c squared. Okay? Now that I have all of this stuff, I can go through and start filling in information, right? So first, what is cosine theta? Cosine theta should be, and I know this is weird because you're like, oh no, I need to use my calculator to find out what theta is. We don't, because based on this triangle, the cosine of theta should be the adjacent over the hypotenuse. This should be 5 over 13 times, now d theta dt is what I need to solve for, so we'll leave that there. That equals, now I start filling these things in. C is 13, dB dt was negative 0.5, b was 12, but dc dt was 0, and we end up dividing by 13 squared. And so now really this is just sort of a matter of simplifying things out. 5/13 d theta dt equals, there's actually some interesting things happen over here. This turns into 0, then one of these 13s will divide out, and I'm ending up with negative 0.5 over 13. So when I multiply both sides by 13 over 5, these divide out, these divide out, these divide out, and I end up with just d theta dt equals negative 0.5 over 5, which is basically negative 1/10. So, and the units for this, by the way, would be radians per second. So what it means is that angle down there is getting smaller at a rate of negative 1/10 of a radian per second. These problems are a little bit tricky to begin with, but it all hinges around the idea of if you can make a good diagram and label it, write your equation and take a derivative, you'll be able to get to the answer.